Hi everybody, welcome to another video in pre-calculus section 8.6. So this will be very similar to what we have in section 8.4. We study about vectors, but this time it is vector in space, meaning that a vector in 3 dimensions. Pretty much everything we have up to this point is from 2 dimensions. We just go to 3 dimensions. There's not much difference. Right. So in the plane, each point is associated to the order pair. Now, in space, we have the order triplet. So have 3 components, x, y, and z in the rectangular coordinates. And of course, x-axis, the y-axis, and the z-axis all perpendicular to each other. Now, we talk about the vectors in space later. Now we focus on a point in space, a point in 3-dimensional space, to be more precise. So we have 3 axes, the x-axis, the y-axis, and the z-axis, all of them perpendicular to each other. So we have the x-axis, the y-axis. I only draw the positive. Of course, the negative y-axis will be on the other direction, and the z-axis is this. And we cannot interchange the x and y in that order. So x, y, and z. So how did that work? Actually, we will learn later on. This is the right hand rule. So let's say originally we have if we're going to draw the x and the y-axis like this, then what will be the z-axis? Well, the z-axis in that case is going to be pointing out of the page, will be this, and all 3 of them are perpendicular to each other. So now if I use the pen, will be like this: x-axis, the y-axis, and the z-axis will be perpendicular to this. Let me zoom out so you have the better idea. Okay, so x, y, and z. So how did that work? This is the right hand rule. The right hand rule say put the hand in the direction of the first component. So this is going to be this. And then second, if you curl the fingers in the other direction, and then the thumb will indicate the third direction. So now if we have this x, y, z like this, of course you can rotate, put the hand in the direction of the first, which is x, curl the finger in the second direction, and the thumb will indicate the third direction. So in that case, the z-axis will point out of the page. Now, of course, if we switch like this, x and y, if we write x and y, so put the fingers in this, and then curl on the second, and then the third, so that pointed out. If we interchange y and x into this, if this is the case, put the fingers in the first direction, put the hand in the first direction, and then curve in the second. Of course, you cannot do that. Cannot bend the finger backward. So you cannot do that. In that case, you turn the hand, and that is the first direction, and then we curve the finger in the second. In that case, the thumb point down. So that is point into the page. So if this is the case, z will point down. So x, y, and z must obey the right hand rule. The x is direction of the hand, and then rotate the fingers in direction of y. The thumb will indicate the z direction. Right. As long as we have that, it should be fine. We revisit this later. Right. Now let's say if we want to plot the point, for example, how do we plot 1, 2, and 3? So that means we have 1 on the x-axis, 2 on the y-axis. So this is the point 1 and 2. Now we have to write all the point in a three-dimensional space, meaning the point will have 3 components. So we have one more component. This on the xy plane, so it will be 0. Now if we want to write 1, 2, and 3, from that point we go up 3 units. So this is the point 1, 2, and 3. Of course, we cannot just put a point there and say 1, 2, 3. We have to write, kind of draw that on the xy coordinate, and then draw the line to go up here 3 units. So we know that actually go up 3 units for z. So that's what we have. Right. Now, once we have that, we'll define the distance between 2 points in the three-dimensional space. Now, if we only have 2 components, this is the distance between 2 points in the plane, in 2-dimensional plane. And this is the distance between 2 points in 3-dimensional space. Right, so simple enough. So pretty much we subtract the x square, and then subtract the y square, and then subtract the z square, add all of them under square root. So this is also called the 3-dimensional Pythagorean theorem, if you will. Right. So if you want to find the distance between the 2 points, have the square root of the x minus the x's. Doesn't matter which one minus which, because for example, if we have 1 minus 3 square, that is 2 square, or 3 minus 1 square, that is also 2 square. Negative 2 square or 2 square, both of them equal each other. So I just take x minus the x. Let's use 2 minus 1, so we have 3 minus negative 2 square plus y minus the y square, and the z minus the z. So 3 minus negative 2, that's 5 square, 25. Minus 4 minus 5 square, minus 9 square. 9 square is 81. And 6 minus 1 is 5 square, is 25. 25, 25, 50, 81. That's square root of 131. Right, simple enough. So that is the distance between 2 points in 2-dimensional space. Now we go to vectors in 3-dimensional space. On the previous section, in particular section 8.4, we say that vectors and a point kind of associate to each other. That is, if we let the tail end of the vector to be at the origin, then the point, the head of the vector is just a point. So we associate a vector by a point where the head of the vector is at the point. So 3 components pretty much for a point, and then 3 components for a vector as well. Right. And also we introduced positive r and j. We did have r and j for the positive x and positive y axis. Now we have k, positive x axis, positive y axis, and positive z axis. Pretty much in this x, y, z, we all obey the right hand rule. Now, if a vector v in space with initial point at the origin, same thing. The terminal point, the end point is at ABC. Then we can represent vector v in terms of vector rjk as follows. So now we can write a vector in 3 components, rjk, or we can write using the angular bracket notation. Right? So pretty much now we just add 1 component to a vector. Now, a vector whose initial point is the origin is called the position vector. Of course, we'll talk about that. Now, once we have the position vector, then we say a vector connecting 2 points, the vector v is equal to the vector p1, p2, if we just take the point p2 minus the coordinates of p1, and we turn that into the vector. So vector v is equal to p1 p2. The vector connecting p1 p2 p1 to p2 will be p2 minus p1, so it's always a final point minus initial point. So, and then we can write ijk component or angular bracket notation. Right, now let's do some math of three-dimensional vector. Of course, same thing. Two vectors are equal if the components are equal. We can add the two vectors, subtract two vectors, multiply by a scalar. In which case, of course, we can write this in angular bracket notation, and then the magnitude of the vector is square root of the square of the component. So Pythagorean theorem. Now the point here is this is a vector in space, even though we cannot visualize vectors in fourth or higher dimension. If we want one more component, it will be I, j, k, and then more components to it. So for example, if we have the vector in three-dimensional space, we may have that. If we have four-dimensional space, just add one number to it, one more component, and this is the vector in four-dimensional space. Like I said, we cannot visualize vector in four dimension because we are three-dimensional creatures, so we won't be able to see it. But the math we can do it easily. We can add the vector three-dimensional space, four-dimensional, and we just add component wise. Of course, we can extend this to any higher dimension space for vectors, and the math is still the same. We just add components to it. So add the third dimension to it, we have all the operation in three-dimensional space. Of course, same thing. The magnitude of this vector is equal to 1 square plus 2 square plus 3 square plus 5 square all under square root. So this is a four-dimension. Pythagorean theorem also works. Even we cannot visualize, the math still works. Right, now let's say we have this three vectors, two, vector v and vector w, 5v plus 3 times w. So vector v will be 3, negative 2, and 4. We add 3 times vector 5, 7, and 2. Right, let's multiply the 3 into all of the components of the vector w first. So 15, 21, and 6. And then when we add the vector, we add the components. 3 plus 15, negative 2 plus 21, and 4 plus 6. So we have 18, 19, and 10. Once again, if we want to use calculator, we use this second parentheses, and then we have 3, comma, negative 2, and 4. So this is a list of 3 numbers. Or the vector has 3 components. A point has 3 components. Right, 3 times the second vector, 5, comma 7, comma 2. Close. Yeah, that's what we have. So simple enough. And when we subtract the component v, subtract w, so 3 minus 5 minus 2 minus 7, 4 minus 2. So we will have minus 2, minus 9, and 2. Of course, if we want to subtract them, I highlight that. Instead of plus 3 times, I just subtract them. And that's what we have. So simple enough. Now, the magnitudes of the vector will be the same. Square root. Let me write this properly. First, we want the magnitude of the vector W 5, 7, and 2. So square root of the square of the component. 5 square, 7 square, and 2 square. All of them add up, all of them up and under square root. So 5 square, 7 square, and 2 square. We have 78. And I'm just going to leave it at square root of 78 because 78 is 3 times 26, and we cannot really bring down anything outside square root. So that's what we have. Right. Next, for any non-zero vector v, the vector u equal to v divided by v is the unit vector. Once again, the unit vector has the length equal to 1 and has the same direction as v. So this vector u is the same direction as v, but the length of u is equal to 1. Therefore, we use u for that. Now, let's say find the unit vector in the same direction as v. By the way, that sounds like a long-winded word, right? So usually when we say that, we just say normalize vector v. Right. Later on, if we want to do the simplify, instead of find the unit vector in the same direction as v, we can just say normalize v. Normalize vector v. So we find the vector in the same direction as v. Okay, we'll do that. Okay, it's not even a discussion. Right. Now, if we want to normalize v, we take the vector v divided by its magnitude. So we have the vector 6, -2, and 9. The magnitudes of that is Pythagorean theorem, 6 square plus -2 square plus 9 square. We still have 6, -2, and 9 on the top. At the bottom, 6 square, -2 square, or just 2 square. That's like 40, and 9 square. So 121. Square root of 121 is 11. So this is 11. So the vector divided by 11, meaning each component will divide by 11, and we have the vector 6 over 11, -2 over 11, and 9 over 11. Of course, we can leave the answer in this, or we want to find write as ijk will be 6 over 11 times I, the vector I, plus, or we can just say -2 over 11. Times vector j and 9 over 11 for vector k. Right, so that's good. Right, everything like what we have earlier, except now we have 3 dimensions. We just add 1 dimension into it. Now the dot product will be the same. This is the dot product of 2 vectors in 2-dimensional plane. We just add 1 component to it, and then we have the dot product in 3 dimensions. Of course, we can define the dot product for 4th, 5th, or higher dimension the same way. Right, let's do the math. Let's do some example. Let V be 6, negative 2, and 9, and W 2, 3, and negative 4. Find the dot product of V dot W. Vector V 6, negative 2, and 9. Dot with 2, 3, and negative 4. 6 times 2. Negative 2 times 3. And 9 times negative 4. That is 12 minus 6 and minus 36. Right, so 12 minus 6 is 6 minus 36. That is 30. 12 minus 42 is 30. Right, simple enough. Now W dot V. W 2, 3, and 4 dot V 6, negative 2, and 9. So 2 times 6 is 2 times 6. 3 times negative 2. Yeah, if I copy it right, 2, 3, and negative 4, right? And then negative 4 times 9. So once again, we have 12 minus 6 minus 36, which is also 30. Right, as you see, because the way we define the dot product, we can interchange this, the product of each components, the product of corresponding components, and then we add them. So all of the multiply and addition are commutative. The dot product is also commutative. So that's what we have. And now the dot product of W by itself, 2, 3, and negative 4 dot 2, 3, and negative 4. So 2 times 2, 3 times 3, and negative 4 times negative 4. So 4, 9, and 16. And that gives us 26. Yeah, I mean 29. By the way, you can write 2 square, 3 square, and 4 square. So what's that look like? Notice that if we write the magnitudes of W, that magnitudes of W, W is 2, 3, negative 4. So we have 2 square plus 3 square plus negative 4 square. Right? So this is the magnitudes of vector W. And this is pretty much the same thing, except this one have no square root. So we can say the magnitudes of the vector W equal to square root of the dot product of W by itself. Or later on, we write the dot product is equal to the square of the magnitude. Right. Of course, all of these properties we have in 2-dimensional vector. Now will be the same thing for higher dimension vectors. Dot product is commutative and also distributive properties. The dot product of a vector to itself is the magnitude square, and a zero vector dot with any vector is equal to a zero number. In the same way, we define the angles. The angles between 2 vectors is the dot product over the product of the magnitudes. Or if we multiply both sides, we have the product. The dot product is equal to the product of the magnitude. By the way, do not write anything between the magnitude of u and magnitude of v, and then cosine of the angle in between. So simple enough. Now let's find the angle between u and v. So I will use this formula, cosine of the angle between two vectors u dot v over the magnitudes of the product u and v. So u 6, -2, and 9. So vector u dot vector v 5, 1, and -4 over the product of the magnitude. The magnitude will be 6 square, -2 square, and 9 square times the product 5 square, 1 square, and -4 square. So 6 times 5, 30, -2 times 1, -2, and 9 times -4, -36. That's what we have on the top. 30 minus 2 minus 36. The bottom, square root 6 square, 6 square plus 2 square or -2 square, same thing. 9 square. So that's the square root of 121. And then 5 square, 1 square or just 1, and 4 square, which is 42. To simplify all of that, we will have on the top 30 minus 2 minus 36, so 30 minus 38 minus 8 on the top. The bottom we have 11 square root of 42. So we have cosine equal to that. So if we want to get back to theta, it is cosine inverse of that. 11 square root of 42. So I will keep the calculator in degree mode. Usually that's when we do inverse trigonometric function. Wait. So in degree mode. Yep. So cosine inverse of a fraction where we have -8 on the top, 11 times square root of 42 at the bottom, and cosine inverse of that 96.44 degrees. Right. Now, what we define next is the directed angles, or direction angle. Sorry, direction angle will be alpha, beta, and gamma, which is the angle made between the vector and the ijk component. So, which is the positive x-axis. So if we have a vector here, so we have the vector made with the positive x-axis, the positive y-axis, and the positive z-axis, alpha, beta, gamma. That, and it can be shown cosine alpha is that. So pretty much cosine adjacent over hypotenuse. So that's why we come up with this components. And of course we multiply on both sides. We have the x component is magnitude of v times cosine of a, and then the y component vector magnitude of v times cosine of beta, and then magnitude of v times cosine of gamma for c. Just multiply on both sides. That's simple enough. And it can be shown that the sum of the square of the direction angles is equal to 1. I'm not focused on that. Now let's just go to an exercise. Now we have vector in 3 dimensions. Now we just find the angle between 2 vectors, and then later on the projection of vector v onto vector w. Right. Now first, the angle between 2 vectors, cosine of an angle is equal to the dot product over the magnitude over the product of the magnitude, that is. So vector v 1, 1 and 1, dot 2, 0 and 3 over the magnitudes of v, which is 1 square, 1 square, 1 square, so that is 3, square root of 3. And then magnitude of w, 2 square, let's just say 0 square and 3 square. Right? So dot product on the top, 1 times 2, 2 plus 1 times 0 plus 1 times 3. The bottom, square root of 1, 1 and 1, that's square root of 3. 2 square and 3 square, 2 square is 4, 3 square is 9, 4 and 9, make that 13. Right, and so we have 5 over 3 square root of 13. So we get theta equal to cosine inverse 5 over 3 square root of 13. Is that in, yes, still in degree mode. Cosine inverse of 5 divided by, if we write like this, make sure we have the parentheses for 3 and square root of 13, like that. So 5 divided by the whole thing here. And we have 62.467, let's just round to 1 decimal places, 62.5 degrees. Right, so that is the angle between 2 vectors. Now let's find the projection. So what is the formula for orthogonal projection? So projection of vector v onto vector w. Right, so we have this back in section 8.5 when we define the dot product. So projection of v onto w is going to be vector v dot vector w over w square times the vector w. So that is the formula for orthogonal projection. Later on we can check later. Right, v is 1, 1 and 1. Now dot with 2, 0 and 3. And then vector w is 2, 0 and 3, so we have a square of the magnitude of w. W is 2, 0 and 3, so we have the square root of 2 square, 0 square and 3 square. So once again the dot product we already did, which is 5. And here we have square of square root of 13. I forgot to multiply by vector w, sorry. Right. Ran out of that, so let's just do the old fraction. Yeah, whatever we have multiplied by the vector 2, 0 and 3, sorry. So dot product give us 5. And this we have the square root of 13 square and vector 2, 0 and 3. So 5 square of 13 square, so it would just be 5 over 13 times 2, 0, and 3. And we multiply that to every component. That gives us 10 over 13, 0, and 15 over 13. So that's the projection of V onto W. Now let's check. Okay, that is the answer of that problem. Now what we have is we have a vector V, and then we have a vector W, and then the projection of V onto W is going to be this vector. Right. Now let's check. What we have is the magnitude of V and the magnitude of projection of V onto W will form the triangle, and this is the angle between the two vectors. Right. So that is the way we can check. So first let's find the magnitude of vector V, which is square root of 1 square, 1 square, and 1 square. So square root of 3. Easy to check. Now find the magnitude of vector of the projection of. By the way, let this be what we defined earlier. For that, we call this is vector V1. So let's V1 be the projection of V onto W, and now let's find the magnitude of V1. Will be that. So square root of 10 square, 10 over 13 square, plus 0 square, plus 15 over 13 square. Right. So 10 over 13 square plus 15 over 13 square. Can we get a fraction? 25 over 13. Right, so that is the magnitude. Now, we know the angle between them is 62.5, right? So if we want to have adjacent over hypotenuse, of course the magnitude, that is, we can check. And the question is cosine of what we have earlier is 62.5 degrees equal to the adjacent over hypotenuse, adjacent magnitudes of V1 over hypotenuse, magnitudes of V. Is that true? So what I do is I'll take cosine of the angle, which of course what we say earlier is 5 over 3 square root of 13. So cosine of the angle is equal to 5 over 3 square root of 13. Well, we did in the first part, right? To get the angle, we just find the cosine inverse. So that's what we have. And now, so what is magnitude of V1 over magnitude of V? So, by the way, this we can write as square root of 25 over square root of 13, or 5 over square root of 13. And now we take this, divide by we seem to miss something, did we? Yeah, I just wrote it wrong. Yeah, I forgot the square root of 3 here. Sorry. So, glad we go back and check it. Right. So, cosine inverse of 5 divided by square root of 3 times square root of 13. That's right. Is 36.8 degrees. Sorry about that. 36.8 degrees. Right. Yeah, I forgot to write the square root there. I'm glad we checked this so we can catch what we missed earlier. So there's a square root of 3, and of course cosine inverse of that is 36.8 degrees. Now we know cosine of that angle is 5 over square root of 3 over square root of 13. Now if we take the magnitudes of V1 over magnitudes of V, we will have 5 over square root of 13 over square root of 3. Of course that gives us 5 over square root of 3 times square root of 13. Of course that equal to cosine of this. So there's a relation between the angle between two vectors and orthogonal projection. Right. Once again, sorry about that. That should have been that should be square root of 3, which I forgot to write. But we go back and check it. Right. And orthogonal projection, still the same thing. So the point of this section is that if we can do all of those, combine the vectors, add the vectors, multiply by scalar number, angle between two vectors, orthogonal projection, all of those things we can do for two-dimensional vectors. We can also do that for three-dimensional vectors or higher dimension. Right, and that's what we have for section 8.6. Thank you for watching, and see you in another video in precalculus.